Welcome to 6.3 using radioactivity. What we're going to talk about today is first radiocarbon dating, and then we're going to talk about nuclear energy, and then finally we're going to talk about radiotherapy. Hopefully this one should be a little bit shorter than last time because that kind of went over. We had to split it into 2 videos. Terrible. Anyway, that's where we are. So what you're looking at here is a picture of ale stones in Start in Sweden, and we happen to know that these stones were assembled in this upright fashion in 56 CE or AD or whatever you want to call it, 56 years after the birth of Christ. Okay, and the reason we know this is because of radiocarbon dating, and it's a really interesting process, and I think it's something that I think we should be very proud of as a people. So how do we do it? We can't date the rocks directly. Okay, we have no way of doing that, but we can date other biological material around the rocks that we know has been that was around the same time as when the rocks were put up. So, like for example, if we found some wooden material that we know was used to stand the rocks up, then we would know that that wooden material was most likely from a tree, and that tree was cut down not too long before the rocks were put up, and therefore we could date the biological material in the tree, and therefore be able to have some idea as to when the rocks were stood up in this fashion. And that's exactly how they did it. Let's have a look at how that works in the next slide. So, plants and animals, they take in carbon-14. Okay? Every day, plants photosynthesize and take in carbon dioxide from the air as a part of that, and turn into oxygen and all the rest. And as a part of that, they refresh their carbon-14. So animals and plants have a constant rate and amount of carbon-14 in their bodies. However, when they die, they stop doing this. Plants stop photosynthesizing and animals stop eating plants and other animals and all this kind of thing that they need to update and refresh their carbon-14 levels. Because they're dead now, they can no longer do that. So from that point, the carbon-14, which is an unstable isotope of carbon, starts to degrade. So by tracking the amount of carbon-14, the proportion of carbon-14 within a biological material, we can see how old that material is. So we take a certain amount, 100 grams of wood. Okay, we calculate the amount of carbon-14 in there, and if there's half as much as there should be, then that would be the half-life. Okay, or a quarter life, or whatever it is. Okay, so looking at this graph, this is carbon-14. And this is the percentage of carbon-14 that remains. And the half-life of carbon-14 is about 5,730 years, which is actually relatively small for, other biological type isotopes. I mean, there are other isotopes in the body we could use, phosphorus, etc., but their half-lives are so much longer that it would make it, far too confusing. But by knowing this half-life is 5,730 and, 11,000, 17,000, 22,000, and 28,000, by knowing this, we can track that and then find out when the biological material was around. Okay, so if we know that the levels are in, wood, I don't know the levels, but let's say they were, supposed to be, 30% or something crazy like that. I don't know if it's that high, but 30%, and we only found that the levels were at 15%, then we would know it would be at half-life, and that biological material was cut down or died 5,730 years ago. Okay, and if it was 20%, it would be some other percentage. Does that make sense? Good. Now, one thing I want to remind you of, now that I've got this graph in front of me, is this 1 half-life, 2 half-life, 3 half-life thing. We talked about it before, but I'm going to remind you again. So 1 half-life is half left, 2 half-life is half of half, which is a quarter left, 3 half-life is a half of a half, which is 1/8 left, and 4 half-life is 1/8, 1 half of a half, which is a 16th, and you know, what are we? 1, 2, 3, 4, 5. 5 half-lives, so a half of a half of a half of a half of a half, which is 132. Okay, good. Next. So, let's look at how we, one application that we always think of when we think about degrading atoms. We think about nuclear reactions, especially in a power, station or a nuclear bomb or whatever else we have. So, this is uranium-235. So uranium-235 is a relatively stable nucleus. Okay, what we do is we add one slow-moving neutron into 235, and this creates such a violent rejection that we ended up dividing this uranium atom into barium-141 and krypton-92. All right, and as a part of that split, this fission, we create 3 neutrons, some gamma rays, and a whole mess of energy that's used to, heat up some cooling fluid, and which heats up some water, which turns some turbines, which, turns my toaster, which burns the toast, and then sets off my smoke alarm. So here, you can see the same thing represented in the scientific notation. Uranium-235 plus 1 neutron, okay, is barium-141, and krypton-92 plus 3 neutrons. Good. Another application is radiotherapy. For example, PET scans. We inject patients with radioisotopes that give out gamma rays. Okay, so they're undergoing some kind of decay that emits gamma rays, and this machine here detects the gamma rays as they come out of the person, and then we can, track where they are and the internal systems of that body. And we can use that to, cure all sorts of diseases from leukemia to whatever else. Okay, just get a good image of it. All right, this is a nice and short and quick one. Excellent, I'm glad. Now, what I want you to do is go to chapter 6.3, have a look at the blue words, go to Quizlet, and put all the words from 6.3 to Quizlet. All right, I'll see you in class.